Hi, my name is Maithili, and I'm currently a junior studying neuroscience and Spanish at Chapel Hill. Something about me is that I'm actually fluent in Spanish, so I've been super fortunate to be able to take this semester abroad to study in Madrid. It has definitely been one of the best experiences of my life. I've been so lucky to do so much traveling, and I've just been learning so much. It's genuinely been a once in a lifetime experience. I love it so much. But it definitely doesn't mean that I've forgotten how much I love chemistry as well, and how much I would love to go back to being in LA when I'm home. So one of the reasons I actually want to be in LA is because I know what a valuable resource they are to chemistry students. I remember that when I was in Orgo, I would definitely attend the majority of the LA sessions just because it was so helpful for me to kind of go over everything that we had talked about in that week and to solidify all the concepts that we had learned and just go over any misconceptions I had. It was just really, really helpful to talk through everything with the LAs, and it's something I really want to be able to give back to the new chemistry students. So something I plan on doing as an LA, something I did the last time I was in LA, is to not just spoon feed the answers to the students, but kind of help them work through the problems on their own. Because I think that this way, the students are able to solidify the concepts in a much more efficient way than just kind of having the answers given to you. I think you are able to retain that kind of information for a much longer period of time, and it's just a much better way of learning overall.
So this is the problem I'm going to be presenting. When I start with problems like these, I like to do some retrosynthesis just to help me figure out what mechanisms are going on. So I see here that we're starting off with a 1,3 dicarbonyl compound that reacts with an alpha-beta unsaturated ketone and a base to form a 6-membered ring and another alpha-beta unsaturated ketone. So this is actually a really good indication of a Robinson annulation, and I know that Robinson annulations are made up of 2 reactions. So first a Michael reaction, and then later an aldol either addition or dehydration. So now that I know where to start, I'm going to form our enolate, which is actually going to act as our Michael donor. It's going to act as the nucleophile, which attacks the beta carbon of the alpha-beta unsaturated ketone. So this OH is actually going to pluck off this alpha proton, kicking up these electrons, and then these to form our enolate. And so when the electrons from the oxygen kick back down, we are free to attack the beta carbon of the alpha-beta unsaturated ketone. So these electrons will shift, and then the carbonyl electrons will go up to the oxygen, forming our enol. Enols now are typically less stable than ketones are, so we're going to undergo a keto-enol tautomerization. And also, the reason I actually labeled these carbons was just so that I don't lose anything, because we're actually adding this entire compound to what we started with, so just to make sure there's no losses, just in case. So we get the reformation of our carbonyl through the tautomerization, and now that we've finished our Michael reaction, we actually can start the aldol part of the Robinson annulation. So the OH minus is going to pluck off this alpha proton, kicking up these electrons here, and then pushing up the electrons onto the oxygen, forming another enolate. So now we can do an intramolecular aldol reaction, and we can do that because there's 6 carbons, so we can form a 6-membered ring, which is very low in energy, very stable. And again, I've labeled all the carbons just so that I don't lose anything. So when you redraw this stuff out here, we are able to reprotonate this oxygen with water, forming a hydroxyl group that hangs off of this carbon. So technically, you could stop here, but the better way to go is to do an E1CB elimination reaction. And that's because when we do an elimination reaction, we're actually able to kick off OH as a leaving group and form a double bond right here, which forms a conjugated system, which makes this entire molecule much lower in energy, much more stable. So what happens is the OH that we had before is going to react with this alpha hydrogen, which is actually going to kick up electrons here, and then we're going to form So these electrons are going to kick up onto the oxygen. So now when the electrons from the oxygen kick back down to reform the carbonyl, the double bond will shift over and in turn kick off OH as a leaving group. So we are actually left with now our final product, and we've also got our the regeneration of our OH.